Okay, today we're going to talk about relative rates of growth, or relative growth rates. It's going to involve L'Hopital's rule, so I'm going to just do a quick warm-up about L'Hopital's rule. If you feel you've got L'Hopital's rule down, feel free to scroll past this warm-up, but it'll only take a second. This particular limit is asking us to find the limit as x approaches 0 of cosine of x minus 1 all over x squared. Again, the fastest way to find one of these limits is just trying to plug in 0. If I plug in 0 to cosine of x, I'll have cosine of 0 minus 1, which is 1 minus 1, that's 0. Plugging a 0 in the bottom, I get 0 over 0. That's a 0 over 0 situation, which is ideal for L'Hopital's rule here. L'Hopital's rule works, again, when you ever have a 0 over 0 situation with your limits, or an infinity over infinity situation. So L'Hopital's rule says that when that happens, I can find the limit much easier by just taking the derivative of the numerator and the derivative of the denominator and then trying the limit again. So derivative of the numerator, derivative of cosine is negative sine of x. Derivative of negative 1 is 0, so that's why it's gone. Derivative of x squared is 2x, so then we try again. Plug a 0 into there, negative sine of 0 is 0. Plug a 0 on the bottom, I still have 0 over 0. Never fear though, L'Hopital's rule still applies, so do it again. Derivative of negative sine will be negative cosine. Derivative of 2x is 2. Trying again, plugging a 0 into there, that'll be a negative 1 over 2. This limit is equal to negative 1/2. That, in the nutshell, was L'Hopital's rule. Today, we're going to talk about something called relative rates of growth. To start us off, we're going to just mention that e to the x is a function that grows really, really quickly. You guys might remember that from pre-calc when we talked about how quickly this function grows and how we said it's one of the fastest growing functions that you've seen at that point. In fact, it's crazy fast. It's so fast, if we graphed it on this board here, after 10 inches, I'd have to go 1/3 of a mile up the y-axis to plot my point. At 44 inches, I'd have to go 2 million light years. And by the time I went 64 inches along the x-axis, I would be at the edge of the known universe, 13 billion light years along the y-axis. It grows crazy fast. Natural log of x is the inverse of e to the x, and that would make sense since it's the inverse. It grows very, very slowly. It's one of the slowest growing functions you've probably seen at this point. It's the exact opposite. If I wanted to reach 64 inches in height along the y-axis, I'd have to go 13 billion light years along the x-axis. It grows crazy slowly. It grows so slowly that sometimes students mistakenly think natural log of x has a horizontal asymptote. It doesn't. It's just grows so slowly that it looks like it does. So how can we tell which one's growing faster and which one's growing slower, other than just like, yeah, duh, that's growing a lot slower? It has to do with limits. And so I'm just going to read through this definition quick, and we're going to try a few. It says, let f of x and g of x be positive for x being sufficiently large. So it just says, hey, as long as if you have a growing function, right, at some point, even if you start in the negative, it's going to eventually get positive. Number 1, f grows faster than g, which is the same as saying g grows slower than f, as x approaches infinity if one of these two things happen. Notice the setup. This is the limit as x goes towards infinity of f of x over g of x equals infinity. If f grows faster, basically trying to divide g is going to be so small in comparison that f is still going to go towards infinity. It's just going to be so big that it doesn't care what g does. That whole limit's going to go towards infinity. On the flip side, if f grew faster and it was on the bottom, then the limit would go towards 0. Because if f grows faster, as x gets big enough, this is going to be a crazy huge number on the bottom. That's going to be relatively small on the top, and something relatively small divided by something crazy huge is going to get closer and closer to 0. So basically, if you want to figure out which function's growing faster, just take the limit as x goes towards infinity. If your answer is infinity, the function on top grows faster. If your answer is 0, the function on bottom goes faster. Then the question is, what if it doesn't go towards infinity and 0? What if it goes just to some constant like 8? F and g are then said to grow at the same rate. So as x goes towards infinity, if you end up getting some limit, then those functions are said to grow at the same rate. That was actually our L'Hopital's rule one. If we compared these ones, we said, hey, which one grows faster? Oh wait, no, it's not L'Hopital's rule, sorry. I should erase this part. It is not this warm-up. See if you can see why. Yes, we do have a limit that's a constant. But the problem here is this was finding the limit as x approached to 0. When we want to talk about rates of growth, we want to look at the limit as x grows towards infinity, because we really want to care about what happens as x gets really, really big, right? Which one grows faster? You got to kind of wait over time and see what happens as x goes towards infinity. So this is the definition for that. All right, so we're going to try one. It says, which do you think has a faster relative rate of growth? Y equals x or y equals 2x? I've done this for a number of years. Students are always saying 2x. Obviously, it grows at double the rate. You can see it right in the equation. So I asked them to prove it. And so we're going to try that right now. We're going to find the limit as x goes towards infinity of 2x over x. Now, if we're right in that this one grows faster, then according to my definition, that limit should be infinity, right? If the top one grows faster, I should go towards infinity. So let's calculate this limit. Try to plug in infinity. 2 times infinity is still infinity. Put infinity there. That's an infinity over infinity situation. Again, ideal for L'Hopital's rule. So we apply L'Hopital's rule, take the derivative of the top, derivative of the bottom. Derivative of 2x is 2, derivative of x is 1. As x goes towards infinity, 2 doesn't care what x is doing, it's going to go towards 2. 1 doesn't care what x is doing, it's going to go towards 1. It's going to go towards 2 over 1, which is 2. It's not infinity, that's just a number. According to our definition, if my limit as x goes towards infinity is just some number, some L, not equal to 0, then they're said to grow at the same rate. According to my definition, y equals x and y equals 2x grow at the same rate. That's important enough. I'm actually going to write it down. Y equals x and y equals 2x grow at the same relative rate. I'm going to say relative because that's going to help us think about why this is true, because it's kind of counterintuitive. People are like, nah, that 2x, if you graphed it, it's got a steeper slope. Steeper slope means it's growing faster. So we're going to kind of help wrap our head around why they have the same relative rates of growth, and then we're going to move on. Won't take but a second. So first off, according to this definition that we've got for faster rates of growth, growing faster does not mean the same as having a steeper slope. They actually grow at the same rate. And this will help us understand why. All right, to make it easier to understand why we say that y equals x and y equals 2x have the same relative rate of growth, we're going to look at a table for each. It can also be helpful to keep that word relative in mind and to think of x as some measurement of time. So right here I've got a table. Well, here's my x values, my y equals x. And at first when you look at it, you're like, yeah, Mr. Anderson, look, it grows faster. This was at 2 and it jumped to 4. That's a movement of 2. This was at 1 and it jumped to 2. That's only a movement of 1. So like this only grew 1, but that grew 2. That grew twice as much. So people intuitively want to say this one grows faster. But when we talk about relative rates, we kind of talk about where you were at before. Like, look where I was at right here, at 1. When x moved to 2, this thing doubled. I'm gonna see if I can just pull a pen out here. Now I went from here to there. My measurement doubled. Take a look where I started here. This one started at a 2. When I moved from x equals 1 to x equals 2, it also doubled. Now let's think about this. If I wanted to double this again and go up to a 4 here, how long would I have to wait? If this was time, right? Let's call this years. 1 year, I'm at $1. 2 years, I'm at $2. How long till I get to $4? Well, this is just y equals x, so 4 equals 4. I'd have to wait to 4 years till I get to $4 to double it again. Let's look at this one. If I wanted to double that again, yeah, it's a bigger number to start with, so doubling it's going to get up to 8. If I wanted to double it again, how long would I have to wait? 4 years. 2 times 4 is 8. You'll notice my doubling pattern, to double this again, and get up to 8, this will be 8 years. To double that one again, and get it up to 16, that'll be 8 years. The doubling pattern is the same. So they each have the same relative rates of growth. So here's our definition for relative rates of growth. Which one grows faster? Which one grows slower? Let's try one more. Which do you think has a faster relative rate of growth? E to the x or x squared? Now, most of you guys might be feeling I'm tricking you at this point. Like, I think it's e to the x. Mr. Anderson said how that's one of the fastest growing functions at the beginning of this lesson, but he scared me before when he did the 2x and the x, and they weren't the same. So maybe you're not sure. If you're not sure, let's just try one. Put one of these on top, one of them in bottom, try to find the limit as x goes towards infinity. In this case, plugging in infinity into both of those, infinity over infinity, ideal L'Hopital rule problem. Take the derivative of both. Derivative of e to the x is e to the x. Derivative of x squared is 2x. Try it again. Plugging in an infinity in both of those, I still end up with infinity over infinity. So try it again. Derivative of e to the x is still e to the x. Derivative of 2x is 2. Plugging in infinity in now gets me infinity divided by 2, but that's just infinity. So according to my definition, when I get infinity, f grows faster, the top function grows faster. So in this case, lost it all, hold on. In this case, e to the x grows faster. E to the x has a faster relative growth rate when compared to x squared. That's all there is to it. We can check one more problem. There's a frequently asked question. Doesn't matter which function you put on top in the numerator, which you put on bottom of the denominator. The answer is no. A lot of people think, hey, wait, why did you put that e to the x on top? You might have been wondering that. Answer, it doesn't really matter. You could have done it the same way here. So here, same function as before. Comparing e to the x to x squared, except this time I put e to the x on bottom, right? You try plugging infinity, you get infinity over infinity. Gonna have to take the derivative. We end up with the same derivatives but flipped. Looks like we're still getting infinity over infinity. So I take a derivative again, and this time when I try to plug in infinity, I end up getting 2 over infinity. But if I've got 2 over a number that's getting bigger and bigger and bigger and bigger, that end result is going to get closer and closer and closer to 0. When I get closer and closer and closer to 0, the faster growing function, f, is on bottom. So I look at my work here and I say, hey, I was getting closer and closer to 0. My faster growing function was bottom. There, the one on bottom was e, go back to my original, the one on bottom was e to the x. That's the one that's growing faster. Same answer as before. All right, you have an assignment to practice some of the stuff. It's section 9.3, 1 through 25, every other odd. Not every odd, every other odd. So it's really not a ton of problems, right? Don't think it's like 7 problems or something, maybe if that. So shouldn't be too bad. Good luck. Talk to you later.